In mathematics, the LP spaces are function spaces defined using a natural generalization of the P-norm for finite-dimensional vector spaces. They are sometimes called Lebesgue spaces, named after Henri Lebesgue, although according to the Bourbaki group they were first introduced by Frigyes Riesz. LP spaces form an important class of Banach spaces in functional analysis, and of topological vector spaces. Lebesgue spaces have applications in physics, statistics, finance, engineering, and other disciplines. The P-norm in finite dimensions. The length of a vector x equals in the n-dimensional real vector space Rn is usually given by the Euclidean norm. The Euclidean distance between 2 points x and y is the length xay2 of the straight line between the 2 points. In many situations, the Euclidean distance is insufficient for capturing the actual distances in a given space. For example, taxi drivers in Manhattan should measure distance not in terms of the length of the straight line to their destination, but in terms of the Manhattan distance, which takes into account that streets are either orthogonal or parallel to each other. The class of P-norms generalizes these two examples and has an abundance of applications in many parts of mathematics, physics, and computer science. Definition: for a real number Pa per mil 1 yen, the P-norm or LP norm of x is defined by the Euclidean norm from above falls into this class and is the 2 norm, and the 1 norm is the norm that corresponds to the Manhattan distance. The La norm or maximum norm is the limit of the LP norms for PAA. It turns out that this limit is equivalent to the following definition. For all Pa per mil 1 yen, the P-norms and maximum norm as defined above indeed satisfy the properties of a length function, which are that only the zero vector has zero length, the length of the vector is positive homogeneous with respect to multiplication by a scalar, and the length of the sum of two vectors is no larger than the sum of lengths of the vectors. Abstractly speaking, this means that Rn together with the P-norm is a Banach space. This Banach space is the LP space over Rn. Relations between P-norms: the grid distance between 2 points is never shorter than the length of the line segment between them. Formally, this means that the Euclidean norm of any vector is bounded by its one norm. This fact generalizes to P-norms in that the P-norm xp of any given vector x does not grow with p, xp plus aa per mil currency xp for any vector x and real numbers pa per mil 1 yen and aa per mil 0 yen. For the opposite direction, the following relation between the 1 norm and the 2 norm is known. This inequality depends on the dimension n of the underlying vector space and follows directly from the Cauchy-Schwartz inequality. In general, for vectors in Cn where 0, r, p. When 0, p less than 1. In Rn for n greater than 1, the formula defines an absolutely homogeneous function of degree 1 for 0, p less than 1. However, the resulting function does not define an f-norm, because it is not subadditive. In Rn for n greater than 1, the formula for 0, p less than 1 defines a subadditive function, which does define an f-norm. This f-norm is homogeneous of degree p. However, the function defines a metric. The metric space is denoted by ONP. Although the p-unit ball BNP around the origin in this metric is concave, the topology defined on Rn by the metric dp is the usual vector space topology of Rn, hence ANP is a locally convex topological vector space. Beyond this qualitative statement, a quantitative way to measure the lack of convexity of ANP is to denote by Cp, n, the smallest constant C such that the multiple car BNP of the p-unit ball contains the convex hull of BNP, equal to Bn1. The fact that for fixed p less than 1 we have showed that the infinite-dimensional sequence space AP defined below, is no longer locally convex. When p equals 0, there is one A0 norm and another function called the A0 norm. The mathematical definition of the A0 norm was established by Banach's theory of linear operations. The space of sequences has a complete metric topology provided by the F-norm, which is discussed by Stefan Rollwich in metric linear spaces. The A0 normed space is studied in functional analysis, probability theory, and harmonic analysis. Another function was called the A0 norm by David Dunford, whose quotation marks warn that this function is not a proper norm. A is the number of non-zero entries of the vector x. Many authors abuse terminology by omitting the quotation marks. Defining O equals 0, the zero norm of x is equal to. This is not a norm because it is not homogeneous. Despite these defects as a mathematical norm, the non-zero counting norm has uses in scientific computing, information theory, and statistics. Notably in compressed sensing and signal processing and computational harmonic analysis. The p-norm in Countably infinite dimensions. The p-norm can be extended to vectors that have an infinite number of components, which yields the space A0P. This contains as special cases, AA01, the space of sequences whose series is absolutely convergent, AA02, the space of square-summable sequences, which is a Hilbert space, and AA0A, the space of bounded sequences. The space of sequences has a natural vector space structure by applying addition and scalar multiplication coordinate by coordinate. Explicitly, the vector sum and the scalar action for infinite sequences of real numbers are given by. Define the p-norm. Here, a complication arises, namely that the series on the right is not always convergent, so for example, the sequence made up of only ones will have an infinite p-norm for one a permale currency p, A. The space AA0P is then defined as the set of all infinite sequences of real numbers such that the p-norm is finite. One can check that as p increases, the set AA0P grows larger. For example, the sequence is not in AA01, but it is in AA0P for p greater than 1, as the series diverges for p equals 1, but is convergent for p greater than 1. One also defines the A norm using the supremum and the corresponding space AA0A of all bounded sequences. It turns out that if the right-hand side is finite, or the left-hand side is infinite. Thus, we will consider AA0P spaces for one a permale currency P a permale currency A. The p-norm thus defined on AA0P is indeed a norm, and AA0P together with this norm is a Banach space. The fully general LP space is obtained as seen below by considering vectors, not only with finitely or countably infinitely many components, but with arbitrarily many components. In other words, functions. An integral instead of a sum is used to define the p-norm. LP spaces. An LP space may be defined as a space of functions for which the pth power of the absolute value is Lebesgue integrable. More generally, let one a permale currency P, A and be a measure space. Consider the set of all measurable functions from S to C or A whose absolute value raised to the pth power has finite integral, or equivalently, that. The set of such functions forms a vector space, with the following natural operations. For every scalar I, that the sum of two pth power integrable functions is again pth power integrable follows from the inequality. This comes from the convexity of 4. In fact, more is true. Minkowski's inequality says the triangle inequality holds for AP. Thus the set of pth power integrable functions, together with a function AP, is a semi-norm vector space, which is denoted by. This can be made into a norm vector space in a standard way. One simply takes the quotient space with respect to the kernel of AP. Since for any measurable function a we have that a p equals 0 if and only if a equals 0 almost everywhere, the kernel of AP does not depend upon p. In the quotient space, two functions a and g are identified if a equals g almost everywhere. The resulting norm vector space is, by definition, for p equals a, the space La, S, I1/4 is defined as follows. We start with a set of all measurable functions from S to C or A which are essentially bounded, that is bounded up to a set of measure 0. Again two such functions are identified if they are equal almost everywhere. Denote this set by La, S, I1/4. For a function a in this set, its essential supremum serves as an appropriate norm. As before, if there exists Q, A such that a euro phi euro a la, S, I1/4 a copyright LQ, S, I1/4, then for 1 a per mil currency P a per mil currency a, LP, S, I1/4 is a Banach space. The fact that LP is complete is often referred to as the Riesz-Fisher theorem. Completeness can be checked using the convergence theorems for Lebesgue integrals. When the underlying measure space S is understood, LP, S, I1/4 is often abbreviated LP, I1/4, or just LP. The above definitions generalize to Bochner spaces. Special cases, similar to the AP spaces, L2 is the only Hilbert space among LP spaces. In the complex case, the inner product on L2 is defined by. The additional inner product structure allows for a richer theory, with applications to, for instance, Fourier series and quantum mechanics. Functions in L2 are sometimes called quadratically integrable functions, square integrable functions or square summable functions, but sometimes these terms are reserved for functions that are square integrable in some other sense, such as in the sense of a Riemann integral. If we use complex-valued functions, the space L is a commutative C algebra with pointwise multiplication and conjugation. For many measure spaces, including all sigma finite ones, it is in fact a commutative von Neumann algebra. An element of L defines a bounded operator on any LP space by multiplication. For 1 a per mil currency P a per mil currency the AP spaces are a special case of LP spaces, when S equals n, and I1/4 is the counting measure on n. More generally, if one considers any set S with the counting measure, the resulting LP space is denoted AP, S. For example, the space AP, Z, is the space of all sequences indexed by the integers, and when defining the P-norm on such a space, one sums over all the integers. The space AP, N, where N is the set with n elements, is a N with its P-norm as defined above. As any Hilbert space, every space L2 is linearly isometric to a suitable A2, I, where the cardinality of the set I is the cardinality of an arbitrary Hilbertian basis for this particular L2. Properties of LP spaces, dual spaces. The dual space of LP, I1/4 for 1, P, A has a natural isomorphism with LQ, I1/4, where Q is such that a euro 1/P plus 1/Q equals 1. This isomorphism associates G a LQ, I1/4 with the functional IP, G, LP, I1/4, defined by. The fact that IP, G, is well-defined and continuous follows from Haar paragraph LDER's inequality. I par LQ, I1/4 LP, I1/4 is a linear mapping which is an isometry by the extremal case of Haar paragraph LDER's inequality. It is also possible to show that any GLP, I1/4, can be expressed this way, that is, that IP is onto. Since IP is onto and isometric, it is an isomorphism of Banach spaces. With this isomorphism in mind, it is usual to say simply that LQ is the dual of LP. For 1, P, A, the space LP, I1/4 is reflexive. Let IP be as above and let IQ a LP, I1/4 LQ, I1/4 be the corresponding linear isometry. Consider the map from LP, I1/4 to LP, I1/4 A, obtained by composing IQ with the transpose of the inverse of IP. This map coincides with the canonical embedding J of LP, I1/4 into its bidual. Moreover, the map JP is onto, as composition of two onto isometries, and this proves reflexivity. If the measure I1/4 on S is sigma finite, then the dual of L1, I1/4 is isometrically isomorphic to La, I1/4 onto L1, I1/4 The dual of La is subtler. Elements of La, I1/4, can be identified with bounded sign finitely additive measures on S that are absolutely continuous with respect to I1/4. See bar space for more details. If we assume the axiom of choice, this space is much bigger than L1, I1/4 except in some trivial cases. However, Saha and Schiller proved that there are relatively consistent extensions of Zermelo-Fraenkel set theory in which the dual of AA is a 1. Embeddings, colloquially, if 1 a per mole currency P, Q a per mole currency A, then LP, S, I 1/4 contains functions that are more locally singular, while elements of LQ, S, I 1/4 can be more spread out. Consider the Lebesgue measure on the half-line. A continuous function in L1 might blow up near zero but must decay sufficiently fast toward infinity. On the other hand, continuous functions in La need not decay at all but no blow-up is allowed. The precise technical result is the following: let 0 a per mole currency P, Q a per mole currency A. LQ, S, I 1/4 LP, S, I 1/4 if S does not contain sets of arbitrarily large measure, and, let 0 a per mole currency P, Q a per mole currency A. LP, S, I 1/4 LQ, S, I 1/4 if S does not contain arbitrarily small sets of non-zero measure. In both cases the embedding is continuous, in that the identity operator is a bounded linear map from LQ to LP in the first case, and LP to LQ in the second. Indeed, if the domain S has finite measure, one can make the following explicit calculation via Jensen's inequality. The constant appearing in the above inequality is optimal, in the sense that the operator norm of the identity E a LQ, S, I 1/4 a LP, S, I 1/4 is precisely the case of equality being achieved exactly when a euro phi euro equals 1 I 1/4 AE. Dense subspaces. Throughout this section we assume that 1 a per mole currency P, A. Let be a measure space. An integrable simple function a euro phi euro on S is one of the form where alg is scalar and alg ai pound is finite measure, for j equals 1. N. By construction of the integral, the vector space of integrable simple functions is dense in LP, S, I pound, I 1/4. More can be said when S is a metrizable topological space and I pound its Borel I-floor in a Euro algebra, that is, the smallest I-floor in a Euro algebra of subsets of S containing the open sets. Suppose V(S) is an open set with I 1/4, V, A. It can be proved that for every Borel set I pound contained in V, and for every I micron 0, there exists a closed set F and an open set U such that it follows that there exists I continuous on S such that if S can be covered by an increasing sequence of open sets that have finite measure, then the space of par euro integrable continuous functions is dense in LP, S, I pound, I 1/4. More precisely, one can use bounded continuous functions that vanish outside one of the open sets Vn. This applies in particular when S equals Rd and when I 1/4 is the Lebesgue measure. The space of continuous and compactly supported functions is dense in LP, Rd. Similarly, the space of integrable step functions is dense in LP, Rd. This space is the linear span of indicator functions of bounded intervals when d equals 1, of bounded rectangles when d equals 2 and more generally of products of bounded intervals. Several properties of general functions in LP, Rd, are first proved for continuous and compactly supported functions, then extended by density to all functions. For example, it is proved this way that translations are continuous on LP, Rd, in the following sense. Where applications, LP spaces are widely used in mathematics and applications. Hausdorff-Euro-Young inequality, the Fourier transform for the real line, maps LP, R, to LQ, R, to AQ, where 1 AA per mole currency par per mole 2 currency and 1/par plus 1/QA equals 1. This is a consequence of the Riesz-Thoren interpolation theorem, and is made precise with the Hausdorff-Euro-Young inequality. By contrast, if par 2, the Fourier transform does not map into LQ. Hilbert spaces are central to many applications, from quantum mechanics to stochastic calculus. The spaces L2 and A2 are both Hilbert spaces. In fact, by choosing a Hilbert basis, one sees that all Hilbert spaces are isometric to A2, E, where E is a set with an appropriate cardinality. Statistics. In statistics, measures of central tendency and statistical dispersion, such as the mean, median, and standard deviation, are defined in terms of LP metrics, and measures of central tendency can be characterized as solutions to variational problems. Lp, let be a measure space. If 0, p less than 1, then Lp, I1/4 can be defined as above. It is the vector space of those measurable functions a phi such that, as before, we may introduce the p norm a phi p equals np, a phi 1/p, but a p does not satisfy the triangle inequality in this case, and defines only a quasi-norm. The inequality a per mole currency or p plus bar p, valid for a ba per mole 0 yen implies that. And so the function is a metric on Lp, I1/4. The resulting metric space is complete. The verification is similar to the familiar case when pa per mole 1 yen. In this setting Lp satisfies a reverse Minkowski inequality, that is for u, v in Lp. This result may be used to prove Clarkson's inequalities, which are in turn used to establish the uniform convexity of the spaces Lp for 1, p, a. The space Lp for 0, p less than 1 is an F-space. It admits a complete translation invariant metric with respect to which the vector space operations are continuous. It is also locally bounded, much like the case pa per mole 1 yen. It is the prototypical example of an F-space that, for most reasonable measure spaces, is not locally convex. In p or Lp, 0, 1, every open convex set containing the 0 function is unbounded for the p quasi-norm. Therefore, the 0 vector does not possess a fundamental system of convex neighborhoods. Specifically, this is true if the measure space S contains an infinite family of disjoint measurable sets of finite positive measure. The only non-empty convex open set in Lp, 0, 1, is the entire space. As a particular consequence, there are no non-zero linear functionals on Lp, 0, 1, the dual space is the zero space. In the case of the counting measure on the natural numbers equals p, the bounded linear functionals on p are exactly those that are bounded on 1, namely those given by sequences in a. Although p does contain non-trivial convex open sets, it fails to have enough of them to give a base for the topology. The situation of having no linear functionals is highly undesirable for the purposes of doing analysis. In the case of the Lebesgue measure on Rn, rather than work with Lp for 0, p less than 1, it is common to work with the Hardy space p whenever possible, as this has quite a few linear functionals, enough to distinguish points from one another. However, the Hahn-Banach theorem still fails in p for p less than 1. LO, the space of measurable functions, the vector space of measurable functions on is denoted LO, S, I1/4. By definition, it contains all the Lp, and is equipped with the topology of convergence in measure. When I1/4 is a probability measure equals 1, this mode of convergence is named convergence in probability. The description is easier when I1/4 is finite. If I1/4 is a finite measure on, the zero function admits for the convergence in measure the following fundamental system of neighborhoods. The topology can be defined by any metric d of the form, where I is bounded continuous concave and non-decreasing on 0, a, with I, 0, equals 0 and I, t, 0 when t greater than 0 equals min, t, 1. Such a metric is called La copyright V metric for LO. Under this metric the space LO is complete. The space LO is in general not locally bounded, and not locally convex. For the infinite Lebesgue measure I on Rn, the definition of the fundamental system of neighborhoods could be modified as follows. The resulting space LO, Rn, I coincides as topological vector space with LO, Rn, G, x, a d, x, for any positive I integrable density G. Weak Lp, let be a measure space, and F a measurable function with real or complex values on S. The distribution function of F is defined for tar 0 by. If F is in Lp, S, I1/4 for some p with 1 per mole currency par, then by Markov's inequality. A function f is said to be in the space weak Lp, s, I1/4, or Lp, w, s, I1/4, if there is a constant ∀0 such that, for all τ0. The best constant C for this inequality is the Lp, w norm of f, and is denoted by the weak Lp coincide with the Lorentz spaces Lp, A, so this notation is also used to denote them. The Lp, w norm is not a true norm, since the triangle inequality fails to hold. Nevertheless, for f and Lp, s, I1/4, and in particular Lp, s, I1/4 Lp, w, s, I1/4. Under the convention that two functions are equal if they are equal I1/4 almost everywhere, then the spaces Lp, w are complete. For any 0 or Lp the expression is comparable to the Lp, w norm. Further, in the case par1, this expression defines a norm if R equals 1. Hence for par1 the weak Lp spaces are Banach spaces. A major result that uses the Lp, w spaces is the Marcinkiewicz interpolation theorem, which has broad applications to harmonic analysis and to study of singular integrals. Weighted Lp spaces, as before, consider a measure space. Let Ysa, 0, a, be a measurable function. The W-weighted Lp space is defined as Lp, s, y(d1/4), where y(d1/4) means the measure I1/2 defined by, or, in terms of the Radoni-Nikodym derivative, W equals d1/2/d1/4 the norm for Lp, s, y(d1/4) is explicitly. As Lp spaces, the weighted spaces have nothing special, since Lp, s, y(d1/4) is equal to Lp, s, d1/2. But they are the natural framework for several results in harmonic analysis. They appear for example in the Muchin-Hoopt theorem, for 1, p, a, the classical Hilbert transform is defined on Lp, t, I where t denotes the unit circle and I the Lebesgue measure. The Hardy-Littlewood maximal operator is bounded on Lp, Rn, I. Muchin-Hoopt's theorem describes weights W such that the Hilbert transform remains bounded on Lp, t, y(d) and the maximal operator on Lp, Rn, y(d). Lp spaces on manifolds. One may also define spaces Lp, M, on a manifold, called the intrinsic Lp spaces of the manifold, using densities. See also, Balmer-like space, Hardy space, Riesz-Thorin theorem, Har paragraph LDER mean, Har paragraph LDER space, root mean square, locally integrable function, spaces over a locally compact group, Minkowski distance, notes. References: Adams, Robert A. Fournier, John F., Sobol of Spaces, Academic Press, ISBN A978-0-12-044143-3A. Bourbaki, Nicholas, Topological Vector Spaces, Elements of Mathematics, Berlin, Springer Verlag, ISBN A978-3-540-13627-9A. Di Benedetto, Emmanuel, Real Analysis, Berger Currency User, ISBN A3-7643-4231-5A. Dunford, Nelson. Schwartz, Jacob T., Linear Operators, Volume I, Wiley Intersign C. Duran, P., Theory of HP Spaces, New York, Academic Press, Graph Echos, Laukes, Classical and Modern Fourier Analysis, Pearson Education, Incorporated, PPA 253/257, ISBN A0-13-035399 ZAM. Hewitt, Edwin. Stromberg, Carl, Real and Abstract Analysis, Springer Verlag. Coulton, Nigel J. Peck, N. Tenney. Roberts, James W., an F-space sampler, London Mathematical Society Lecture Notes Series 89, Cambridge, Cambridge University Press, ISBN A0-521-27585-7. MRA 808777 Riesz, Frigyes, Untersuchungen 1/4 Bayer System integrierbare Funktionen, Mathematisch Annalen 69, 449 Euro 497, doi, 10.1007/BF01457637 Rudin, Walter, Functional Analysis, McGraw-Hill Science Math, ISBN A978. -0-07-054236-5 Rudin, Walter, Real and Complex Analysis, New York, McGraw-Hill, ISBN A978-0-07-054234-1, MRA 924157 Titchmarsh, E.C., The Theory of Functions, Oxford University Press, ISBN A978-0-19-853349-8. External links, Haswinkel, Michiel, ed., Lebesgue Space, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Proof that LP spaces are complete at planetmath.org.